Quantum mechanics is the science of light and matter, and in particular, how the smallest units of light and matter interact. If you've heard anything about quantum mechanics, you've heard that it's weird.
So in the normal world, your iPhone is either here or it's over there. Your cat is either dead or it's alive. Things have a sort of definiteness to them, which they lose once you go down to the microscopic realm that quantum mechanics describes.
Despite its weirdness, quantum mechanics is incredibly powerful. Indeed, many everyday technologies have their basis in quantum mechanics.
If you want a practical example, I'd say all of modern digital technology and electronics is based on quantum theory.
MRI machines, lasers, GPS apps. Without quantum mechanics, none of these technologies would be possible. How did we arrive at this incredibly strange, incredibly useful theory?
Werner Heisenberg was the first physicist to discover modern quantum mechanics. Before Heisenberg, physicists worked with the atomic model of Niels Bohr. Bohr posited that an atom is like a miniature solar system with a nucleus at the center and electrons swirling around it like little planets. But unlike planets, Bohr proposed that electrons can only exist in very specific energy states around the nucleus, and he linked each state with a classical orbit. According to Bohr's theory, an electron does not emit any light unless it jumps from one of these distinct states to another. Bohr called these stationary states and provided a way to calculate their distinct energies. You can then use these energies to predict the color of the light emitted from the atom. Bohr's model worked splendidly for hydrogen atoms and many positive ions, but for more complicated systems, Bohr's theory failed. One telling case concerned the element helium.
There are two varieties of helium, orthohelium and perihelium, which rarely convert to each other. Try as he might, Bohr couldn't figure out distinct orbital configurations for the two varieties. Bohr's theory also couldn't explain the phenomena of dispersion.
Bohr's right-hand man, the Dutch physicist Hans Kramers. Kramers uses all the machinery of celestial mechanics to derive a formula for dispersion that depends only on observable quantities having to do with transitions between states.
There was no mention of orbits in Kramers' formula. Both helium and dispersion pointed in the same direction, that the orbits were the problem.
Well, Heisenberg then, in a very, very famous paper in 1925, formulates a new theory that does away with these orbits and formulates the entire theory entirely in terms of transition quantities.
Heisenberg's groundbreaking idea to remove the orbits paved the way for quantum weirdness.
Bohr's orbits, well-defined slots in space where electrons could be, are part of what philosophers call ontology. The ontology of a theory gives an inventory of what's really going on in the system, what entities there are, where they are, and what properties they possess. Without the ontology of orbits, what remains are the abstract pieces of the theory, a mathematical description of the states of the system, and mathematical rules governing the evolution of those states over time. This is what we call the dynamics of the theory. We assign a state to the system at any given time, and then monitor the transition of that initial state into future states.
Heisenberg realized that we must break the link between states and orbits. All the successes of Bohr's theory can be retained with the states, while the problematic orbits must be discarded.
You don't see these orbits. What you see is light being sent out when you transition from one orbit to another, and you can measure the frequency of that, and increasingly you can also measure the intensity.
Get rid of the orbits, just talk about what you can tell from the experimental data.
According to Heisenberg, the only quantities that are allowed in a physical theory are those involved in an experiment with a physical system, namely the initial state you prepare the system in, the final state you measure, and the abstract rules of transition between the two.
Ontology means deep down what is an electron, or where is it, or any of those things. Heisenberg certainly would have been allergic to that.
So Heisenberg's breakthrough discovery was that we can sacrifice our knowledge of ontology in favor of dynamics. It is possible to abstract away from the internal goings-on of the atom and focus on assigning states to the system and tracking their transitions.
Heisenberg says he's realized that even in classical physics, the transition amplitudes are sufficient to calculate everything. He said, one can really reduce all interactions between atoms and the external world to transition probabilities. Giving up ontology unlocked the path to the powerful theories of modern quantum mechanics. So it can be beneficial to embrace ignorance about certain aspects of reality in order to bring that reality under control. That's what makes quantum mechanics so weird, but also extremely flexible and useful.
Today, we're seeing early forms of quantum computers which can solve problems that are too complex for traditional computers. Quantum information technology will soon allow us to build secure, unhackable networks. Other sciences are catching up. Some neuroscientists, for instance, are working on abstracting away from neurophysiology and treating neural networks as dynamical systems. My own research explores the possibility of extending Heisenberg's insight to the rest of physics and possibly to the rest of science. Perhaps much of future science will be just as weird as quantum